Today, I will make a video on Lab 5 subroutines in the stack. Um, I'm going to go by this PowerPoint slide provided by one of my good friends, Tim Angela, and shout out to him for this wonderful presentation. Um, a couple of comments about the end of your semester and so on and so forth. The final exam will be in about 3 weeks, 2 weeks, and you will be allowed one sheet of notes, front and back. You can put anything on it. You weren't allowed anything on quizzes, but on the final exam, you will be allowed a exam sheet for everything. If you have any questions, just let me know. I'll try to answer them quickly as possible through email. So also a couple of comments about your lab assignments. Please make your comments not too detailed, but detailed enough to help me understand your thinking and your logic. I believe it is imperative that if you have a clear and succinct inline comments, it will benefit you tremendously in your final exam. So I'll just keep that in mind. I'll try to give you feedback as fast as possible, but just the speed of how this semester is going, it might be a little bit more difficult. But with that said, I'm going to get into Lab 5, and from here on out, I'll just go through the lectures. I'll try to refrain from making it too long for your convenience as well. So I'm just going to get on with it. So Lab 5, subroutines in the stack. Now we're going to get into the bulk of the assembly. And this will be having to do with subroutines and stack organization. Subroutines are basically functions. So what you've been writing in assembly in the .s file, that is your subroutines / functions. In your C code, you might have said like void myfunc with a bunch of stuff into it. That's a subroutine. Two main questions I would like to ask. Two main questions I would like to ask is, what is the stack and what does it do? So if you've been following up on the lectures and have a pretty good idea of what assembly is doing, it is basically memory allocation, where to access those memories. You have the CPU and then main RAM, where you access like global memory, global variables, stuff like that. Now, the stack exists in RAM. So in the stack, you will be storing whatever addresses, values, pointer addresses, etc. But it's a neat way to be able to calculate things really quickly, store things, and utilize those things. And the stacks are pretty relevant in your assignments, and I will get into the structure of how your assembly program is working, and especially later on in this lecture video, you will have the prologue and the epilogue, and you might have been wondering why you had to write the prologue and the epilogue, and in this video I'll try to explain why we do that, and it has something to do with the stack. So without further ado, I will also, please read your lab manual. It is a very good resource if you get stuck. I'll read through it. I know it's a lot of text, but it can give you a lot of pointers, tips, and just little tricks and advice that you need to complete your assignments and understand assembly better. So yeah. So what is the stack? It is a data structure in RAM. And what are the uses of the stack? So it can retain addresses. It can retain, as you see here, like base address, return address, parameters where you want to input certain things before you start a function. And then data values, which you want to use mid-function, like local variables. So how do we utilize or access the stack? We have these two instructions called the push and the pop instructions. So a push places a value inside the stack, and then the pop, it doesn't erase the value, but it takes that value and then stores it into a place that you want. And then specifically how that goes, I will elaborate further later on in this video. And remember this LIFO thing, where it's last in, first out. So what that means is that you got to be pushing values in this order. And we have it set up, we have the stack set up like this, but the top will be the lower address bit. And then as you go down, it'll be the higher address bit. So what happens is that you push a value from the highest to the low, and you get a value here, and then you'll get a value here, and you'll get a value here. So this is the last in, right where I have the cursor at data values. And then so last in, it'll be the first out when you pop it. You're not erasing the value, but you're popping it to a different variable. Let me reiterate. So this value gets popped, this value will get popped, this value will get popped. Okay, so you have three registers to really use the stack. You have the ESS register, you have the ESP register, and then the EBP register. The ESS register is a static register. It is every time a stack is invoked, you have an ESS register pointing to the lowest address available. Now, you can't really, I mean, you can force it to change, but there is no built-in, I can't say that with 100%, thing, but like, we're not going to teach you any built-in ways to really manipulate this. What we are going to be changing is the ESP pointer, the stack pointer register. Now, the stack pointer register holds the value of this address right here. That's why it's pointing to it, and we can gain access to that data. Now, pushes and pops manipulate this register, this pointer. This is how you will grab values. And since this is dynamic, ESP is dynamic, it'll grab values for you, and then it'll quote unquote remove values for you. Now, ESP is kind of indirectly utilized in pushes and pops, and I'll explain that later. The EBP pointer is the base pointer register. It points to a base stack frame. What that means is that it's a reference point for your stack. This stack, I mean, we only have technically 44 bits allocated here, but your RAM can get up to gigabytes of memory. That's a ton of space. So EBP holds a kind of like a reference point. So when your ESP is constantly moving, you have a reference point to go back to. So that's why we use the EBP register. You can get away with not using the EBP register, but it'll get more complex. Number one, push instruction. Push instruction is like your move, add, subtract, divide, multiply, whatever. You have this L right here for bit matching and stuff like that. For our example, let's say the ESS is pointing to the 0 right here, and ESP is, we've set it. We've technically set it to 32. Now push $10 will push 10 into data. So first, step 1, we decrement ESP by 4 bits or 4 bytes. 4 bytes. And ESP, once it's decremented, it'll push the number 10 into the stack. You can push out %EAX. What that does is it pushes the value inside of EAX into where ESP is pointing. Please remember this specific step. It decrements first, and then it pushes 10 into the stack. Now pop, same with push. You can add an L, B, W. But in this case, we can't say like $10. That's not a storing option. So what pop does is grabs the value where ESP is pointing to and then places it into a different place where you can use it. So ESP is pointing to a certain place. When pop is invoked, ESP will always go to the pointing place, grab that 10, and then put it in EAX. And then it increments ESP by 4. It's a good habit to keep track of ESS and ESP. And then in this case, because we placed it into this register, register A will have the value 10. What are subroutines? Like I said, any label can be a subroutine, but it has more to do with functions. And I'm pretty sure you guys are organizing your labels kind of like sub-function stuff. And that's how you probably organize things. And how do we use subroutines? We use unconditional jump instructions, conditional jump instructions, in our cases in the previous labs. But in this case, in this lab, we will introduce you to operands called the call and the ret, which is the return instruction. So in our subroutines, in C code, we have, the main, and inside the main, we have the function 1, and then down here, we usually say, void function 1 or int function 1, float, and then populate it with the code to execute this function. And in assembly using jumps, what we've been doing is that it's not technically main, but it's actually this function here, and then we have one label, we can execute code here, and then jump to here, so on and so forth. We have these jumps, unconditional or conditional. Simply using call is very similar to jumps and labels. So you have main or function name. Then you can invoke a call function 1. And so call operates like a jump. It'll jump to this label, function 1, and then return, as you guess, will return back to what you need. There's a little bit more that goes into calls and returns, but that's the bottom line, simplistic view of calls and returns. So call instruction, what is different in the call instruction? What extra information do you need to know? What extra information do you need to know about ret instructions as well? There's no need for a label in the statement after the function call. Instead, with the call, the return address is remembered. So remember the previous slide, we had call function 1. Ignore this semicolon. Call function 1, and on the next line, you'll have whatever continuing code, assembly code at the bottom, whatever it is. Let's just say. What call does is it remembers or uses actually push L to get this address line. Every single code in your code, this line, this line, this line, this line, it has a memory in your RAM. It's placed in RAM, and this first line, let's say, is at 0. The next line will be at like I think 1, so on and so forth. But it has a memory associated with every single line. So you have a segment for the code, you have the segment for data like global variables, you have a segment for the stack, and then you have a segment for like heaps. You don't really need to know about heaps, but you can basically categorize and organize the RAM into 4 different segments. And so code is placed in RAM like that. So what it does, it grabs this address, pushes it into the stack, and then jumps to the label. So executed call, it'll wherever ESP is pointing. It'll push the return address here. And then, yeah, it'll just stay. So ESP is technically pointing to here. Push L will be utilized, so it pushes up, decrements one place, stores a return address. That's what call does. When read is executed, what it does is ESP was pointing here, but when you call this function read, what it does is it goes to wherever ESP is pointing, pops this value out, increments ESP, and then uses that value as memory and jumps to that memory place. Remember I said it'll use it as memory and memory address. So caution, the return instruction is pretty stupid. It'll always jump to the address it's pointing to. So if this is like a value, like 10, it'll try to jump into address 10 instead of like hexadecimal number like H16. So it is your responsibility to know and keep track of where ESP is so that you can correctly get the RA. Improper access to memory will result in a segmentation fault. Saving register values. So in your quest for calls and returns, there are specific responsibilities that you should keep track of. And we're going to go through a couple of them. But the new function that you're jumping into might need those registers. So more often than not in your main code, you're going to be working on something, and then you're going to find out that you can write a function inside that code that will help speed things up faster. So like, let's say you are organizing your code to find the derivative, but then you need to do some subtraction, some easy quick subtraction. So what you do is you write a function, say simple subtract, and then down outside the main code portion, you will write the code for the subtract function. Now, in that code, you'll have your own local variables, and those variables will be completely independent from the main code. But in our case, we don't have the luxury of just calling random variables everywhere. We have set number of registers that we can use. So because we might be using like register A through D before we invoke this function, um, we need to save those values so that we can use them in our function. That's where the stack comes in. These are referred to as caller and callee responsibility. So caller, the original function in main. Like, so you have like your main code, and then you call simple subtract. So when you call simple subtract, that is the caller. So the caller responsibility should save these three registers: EAX, ECX, EDX, if you're using them. If you're using them previously in the caller, before you do the caller, you got to save EAX, ECX, and EDX so you can use them inside your simple subtract function. Now, please remember, if this is necessary, if you're not using one of these three, you don't have to save it. So the callee function is when it jumps to that label, when it jumps to simple subtract colon, right after that line, you have a callee responsibility to save ESI, EDI, EBX, and EBP. Why? Because I don't know why, off the top of my head, why we do this inside the callee function instead of before the caller function. So when you're doing, say, call my func, you're saving EAX, ECX, EDX before call my func. So you say, technically, if you're using A, C, and D, you say push L, EAX, push L, ECX, push L, EDX, and then say call my func. Now, for callee responsibility, if you're using ESI, EDI, EBX, and EBP before the function, you do when it jumps to the function my func. After you say push L ESI, push L EDI, push L EBX, and push L EBP. That's what we do. I don't know why we split it into like 3 and 4. Maybe it's speed. I can't remember off the top of my head, but I guess organization gets a little bit better. But this is all when ESI, EDI, EBX, and EBP are used before your function, the need for your function. So you're trying to calculate a derivative, and then you find yourself doing these index registers, and then you have something in B, D, C, A, and BP, EBP, then sure. But if you don't have anything inside these things, you don't need to save them because you're not really using them. Okay, so please keep in mind when you execute this, you're gonna, let's say you have something in A and D. So you're gonna push LEAX and then push EDX, and then you're just gonna say call. Remember that there's a return address saved in the middle of all this junk. So you're gonna have RA return address saved, and then you're gonna jump to that portion of the code, and then you're gonna save, if you have something in ESI and EBX, boom, to saved, and then you're gonna execute your code. So as you might have wondered, why do we do prologue, and epilogue? We do prologue and epilogue to set up the stack. The stack is almost imperative for you to utilize RAM efficiently and powerfully. So prologue sets up the stack frame. So it'll set up the ESS, it'll set up the ESP, and the EBP. ESS is already set up for you, so you don't have to say anything, but you're gonna have to, you might have noticed you say like push L EBX, push L EBP, and then move L ESP to EBP. That's the prologue. You're setting up the top, bottom. I mean, technically top of the address, but in our case, the bottom right here. And then ESP will be pointing to the somewhere at the very um, top of this frame, or technically the bottom. The epilogue undoes all that, so that you see last in first out principle in effect. So the standard prologue looks like this: push L EBP, push L EBX, and move L ESP and EBP. So um, the reason why we're doing these is a mix of callee responsibility. Technically, what we're doing in our assignments is that we have a main code in C. That's the driver file. So, and in the driver file, we call our assembly function. And then when the code executes and enters the assembly, or the function name, in lab 3, it was classify. It'll enter classify and go into the .s file. Instead of the .s file, so it call and it enters the .s file. So what it does, so with that call, it saves the return address. It's the same thing. It's a call, so it has to save the return address. And then when you're pushing EBP, we're kind of assuming that the C code was using register EBP. So you need to save it. So EBP is saved, and then you push L. So ESP is here, saved, push L EBX, ESP pushes up here, and then saves the old value of EBX to use. This is standard convention. EBX probably wasn't used in your C, but this is standard convention. You'll never know. So that's why we save the old value of the EBX right here. And then when we move ESP to EBP, EBP is just a free register to put a reference point in the stack. So EBP was pointing somewhat way over here, or like somewhere else. But then we stored that value of where it was pointing to, so that we can use it and replace it and have a placeholder, a reference point right here. Since ESP is right here, we move the address 24 inside EBP. So ESP is pointing here and EBP is pointing here. Now, the next line, sub L $, and this will be a number, size of local variables of ESP. What you're doing is allocating a specific number of spaces for your local variables. So if you are inside your function, inside your subtract function, if you need more variables, like you just need more than the registers A through D and all those indexing registers, then you set up the size of the local variables so that you can store stuff and then utilize stuff from the local variables right here. That's why when you subtract, let's say this is 4 bytes, 8, and then 12. Yeah. So you would say sub L $, 12 ESP, and it'll subtract 12 from 24 and then places it at 12. I'm just saying 12 because there's these 3 boxes right here. 3 boxes. And then so 3 local variables. And then so ESP is pointing here, and then EBP is pointing all the way down here. That's why we needed the reference point EBP, so that ESP can go back to here to replace the old value of EBX and EBP when it returns to the function, and then return as well. local variables, comment about local variables, they don't have a name. They technically don't have a name. They're just a space um, in the stack. Now, this is a very hard concept for a lot of people to get. There is no label associated with this space, but the space, excuse me, the space is technically the label. So this represents local variable A. This represents local variable B. This represents local variable C. Um, so you have to reference this space. You can't say if I have 10 here and I want to utilize 10, um, call like, I mean, technically you can move this variable to A and then say A minus B, like 10 minus B, but that's just, you're moving, what you're doing is you're going from the CPU to this stack, and then you're invoking the CPU to go to someplace else in RAM to allocate A, and then storing 10 all the way down into a different place in RAM, and then utilizing that. You got to initialize A, and it gets messy. You got to initialize that name. So you don't have the luxury of doing that to keep up with all those declarations of variables. So instead of just declaring those variables, you can declare the space. You should have learned how to declare the space in lab 4. So it'll be like movel -4 parentheses percent EBP. Yeah, because it's less than. So it'll go to for less than what it's pointing to, grab that value, then you can move it to a register. You can move this value, or store stuff in here as a placeholder, whatever you want to do. Now epilogue. So EBP was pointing here, remember, and our ESP was pointing here. When we're saying move L EBP to ESP, we are skipping all those local variables and just going back to where we were before we started our code or started our function. So you don't really need to do anything with these values or erase them. You can't erase anything in the stack. So you just move EBP to ESP. What it does is EBP is pointing here, and then ESP will point here. Now, pop EBX, so it'll grab the old value of EBX and place it into EBX, and then decrement 1. And then pop EBP, it'll grab the old value of EBP. EBP is pointing here, but once it grabs that old value, EBP will be pointing somewhere else, like way down here maybe. And then it'll, boom, decrement or increment. And then ret just grabs wherever ESP is pointing and decrement or increments. So it's a return address, and boom, we can return back to our main function or main code and then start executing more things. So if ESP is not in the correct place, we can't grab this RA. And so that's why this movel is very important. So what we covered in this lecture is the stack, subroutines, function calls and returns, stack frames, prologue, and epilogue. Now in your assignments, since you know how to do prologues and epilogues now and what they mean, you are going to be instructed to write the prologues and epilogues. You're more than welcome to copy the previous prologues and epilogues, but in your inline comments, now you must explain to me what this prologue is doing and what this epilogue is doing. So one comment about Lab 5, Assignment 5, is that you're going to have iterative slash recursive functionalities that you need to do. Go to page 103 in the lab manual and read it. It'll help you kind of get a grasp of the recursiveness that can happen with with stacks. And it just speeds up things so quickly. Um, and by utilizing the stack for recursiveness or recursive functions or programs, it makes tasks very easy, very quick to do, um, so on and so forth. The Fibonacci sequence is one example of a recursive mathematical sequence. So the stack is a powerful tool to do these recursive programming. Now, you're going to run into a ton of seg faults if you're not careful with like local variables and how you're placing variables and so on and so forth. But use the GBD debugger to work through those things. The lab manual is there to give you an example as well on the recursive programming and the differences between an iterative programming and recursive programming. Iterative is your for loops and while loops, but recursion is like just putting stacks on stacks on stacks on stacks. I think that's basically it. Yes. Begin Lab 5. You got to compute this Fibonacci sequence for practice manually on a piece of paper, construct a rectangle, and then place those values in the rectangle. Like how register A is getting pushed in, what value is getting pushed in with like numbers 2 or 3. 2 is a good place to start with the Fibonacci sequence. You can look it up online, how to compute the Fibonacci sequence and so on and so forth. Please don't pay attention to this date. This has nothing to do with the summer date, but the quiz will be up for you to do in a couple of days. So don't forget to do your quiz as well. A week, I think. Yeah. But that concludes this lab. If you have any questions, just feel free to contact me and I will try to respond as quickly as possible. Thank you.